This is going to be a quick video going over limiting reagent problems and how to solve some of these. I've seen one of these problems on each of the past exams, the first exam, so it seems like a worthwhile skill. So let's quick go over how we're going to solve these. So it's very straightforward. They're going to give you probably an amount of each of the reactants. Here I just made a little dummy equation, A and B, and you're going to use dimensional analysis to see how much of each product it gives you. So for example, we know we can go through the equation using the stoichiometric ratios. So how this is going to work is, say, I'm going to do this one first. Say I have 1 mole of A, and I know from my ratios here, I know I have, there's a 1 in front of there. 1 mole of A is going to form 1 mole of, this thing, product. So therefore, I would multiply the top, divide by the bottom. This would yield me 1 mole of product. Do the same thing for the other one. 1 mole of B. And here we have a 2, so 2 moles of B give me 1 mole of this product. So, multiply the top, divide by the bottom. This would only give me half a mole of product. So, B then is my limiting reagent. And if you had some system where you were just given 1 mole each, you would get half a mole of product, because that's all that would form. All the B would be used up as soon as you form half a mole of product. So the remaining A wouldn't be able to be used to form more product. So that's the gist of how we're going to solve these. Let's do some exam problems. And coincidentally enough, on 2018, I don't know if it was fall or spring, but on 2 of these 2018 and 2019 exams, it was both problem 3. So, oops. Something to look for, perhaps. Okay, so they give us a reaction. It's the combustion of ethane. How many grams of carbon dioxide are produced if we have 28 grams of the first reactant and 105 grams of the second reactant? So let's essentially do what I just showed you. First of all, they give us the, I'm going to make my marker smaller. They give us the reactants in grams, and we can only go through and do our math to see how many product we're going to get if we're in moles. So let's convert these in moles real quick. To do that, we're going to need the molecular weight. So 28 grams of C2H4 times by, let's see, we're going to want, oh my God, $130 Apple Pencil. And I can't even write. All right, we're going to want grams of C2H4 on the bottom, and then, so this is our molecular weight conversion ratio. And the molecular weight, let's see, 1C equals 12.01, 1H, geez, 1H, oh my goodness. Okay, so therefore the molecular weight is 12.01 times 2, 1.008 times 4, add those up, C2H4 molecular weight equals 28.05. Okay. 28 divided by that, I'm just going to say it's 1 mole. Okay, so we have 1 mole of this reactant. Let me erase all this now. And let's do the same thing for oxygen. We have 105 grams. The molecular weight of oxygen is 32 grams in 1 mole. Grams cancel. And we're going to get 3.28125. Okay. Okay, now we have the moles of reactants. let's just check which one is going to form less product, and that's our limiting reactant. So let's use our stoichiometric ratios. 1 mole C2H4, and then we have 1. We're reacting 1, that's why I wrote this here. And our stoichiometric ratio is 1 to 2. So that would be 2 moles of CO2 formed. And then for the oxygen one, we have 3.28 reacting, and our stoichiometric ratio is 3 to 2. 3 moles O2 to 2 moles CO2. Actually, okay, and that times 2 divided by 3 gives us 2.1875. Of these two numbers, this one's lower, which means the ethane is our limiting reactant. Wonderful. And we already know that that's going to form 2 moles of CO2. And they want how many grams of carbon dioxide are formed. So we just got to convert 2 moles of CO2 into grams. And we're going to use that. Use the molecular weight. Again, molecular weight of CO2 is 12.01 plus 16 times 2, which is 32. 44.01 grams in one. Oh, oops. Okay. See, this is why we use the units, because I wrote it the wrong way. We're going to want moles on the bottom so that those cancel. Yeah. Why? This doesn't matter. I don't know why I'm writing that. Okay. And 2 times 44.01 gives us 88-ish. Okay. And I think I rounded at one point. So that gives us E, which, let's see. I wrote it up here. There we go. Wonderful. Okay. Second problem. Also problem 3. And it's also almost exactly the same. So here we go. The following equation describes the formation of sodium borohydride. How many grams of sodium borohydride are produced if 24 grams of sodium hydride, 24 grams of this, and 96 grams of this. Why does it keep making those lines? So weird. 96 grams of that. Okay, and they want to know how much sodium borohydride we're making, which is this. Okay, so let's do our method. First, I'm actually going to do, yeah, okay, let's just convert first. So 24 grams sodium hydride, the molecular weight of sodium hydride, let me write this. I don't know sodium off the top of my head. So this is going to be, sodium is 22.9, I'm looking at a periodic table, 22.990 at, oh my goodness. Add on the hydrogen, which is 1.08. The molecular weight of sodium hydride is 23 point. Why is it making those lines? That's so weird. 23.998 grams. I'm going to lose my mind. Grams per 1 mole. Put the grams on the denominator. Grams in 1 mole. And 24 divided by nearly 24 is 1. So we have 1 mole. Oh my god. Okay, we have 1 mole of sodium hydride reacting. Wonderful. Okay, erase all this. Do the same thing for whatever that is. Trimethyl borate. Okay, let's we have 96 grams of this. Let's figure out the molecular weight. The molecular mass of boron is 10.811. And then oxygen is 16. Carbon's 12.01. Hydrogen is, it's becoming messy, 1.008. but we have 3 of them, so I'm going to times that by 3. We also have 3 of this whole mess, so let's evaluate that now. 3 times 1.008 plus 12.01 plus 16, times that by 3, then add on boron, which is 10.811. So we have 103.913 grams per mole. Wonderful. Let's convert this to moles. Oh my gosh. 103.913 grams. That's going to be, okay, just under a mole. Okay. Now here, let's just intuitively look. There's a 4 coefficient in front of this sodium hydride and only a 1 coefficient in front of that reagent. And they have nearly the same amount of moles present. This sodium hydride is going to be consumed at 4 times the rate. So in the time that this reaction is going to go through 1 mole of sodium hydride, it'll only go through about 0.25 of the second reagent there. So sodium hydride is definitely going to be our limiting reagent because it's consumed way quicker, and yet we have nearly the same amount of both of our reactants. And if we were to do the more exhaustive method, you'd see the same thing. So now let's convert this using our stoic ratios into sodium borohydride, grams of sodium borohydride. So we're reacting 1 mole of this, and we know that 4 moles are consumed for every 1 mole of sodium borohydride. And in 1 mole of sodium borohydride, how many grams are there? Let's see. Molecular weight of sodium borohydride. Oh my gosh, it's going crazy. Okay. Why does it make those lines? Okay. Anyways. Sodium is 22.990. Boron is 10.8. And we have 4 hydrogens. Four times 1.008 plus 10.811 plus 22.990, 37.833 grams per mole. Chuck that in up there. Okay, multiply everything on the top, which is just 37, divide by everything on the bottom, which is 4. So 37.833 divided by 4. This is going to equal 9.5 grams, which is A. Let's see. Oh, we got A. Wonderful. Excellent A. Hope this helps.